thank you. First of all, this is joint work with a lot of people from the Datum team and Eric Breck at Google and Stephen, who's since moved on to Keist. All right. The motivation for this work is from the rules of machine learning. So specifically, oh goodness, hold on, I'm just realizing that that's in your way. The rules of machine learning, and specifically one of them, which was watch for silent failures. So imagine you're in a very different world and you're building an email system, right? And so one of your users sends an email to another user, but it vanishes into the ether. So what happens? Well, Alice asks, hey, did you get my email? And then Bob replies, what email? And then they actually figure out that your system is broken, they complain to you, and it gets fixed. This is a very different situation than what we face in machine learning. Our machine learning algorithms tend not to be smart enough to realize that the data that they're getting is garbage. They can't identify that the training data is not the same as the data that you're getting at inference time. These are all very difficult to do. So in particular, we should be watching for silent data failures. But how do we do that? And that's what this talk is all about. So as a motivating example, I want to talk about Google Play. So Google Play does some awesome machine learning, and they're launching multiple models every year. But then one time with one model, they did some statistical analysis, and they just realized that they had this very simple mistake where they were missing features at inference time, right? When they were trying to make classifications. And so then they fixed it, and then they got a 2% lift, which was way better than any of the fancy models that they've been launching that had improved the system. So just simple fixes can do amazing things for your system, okay? Now, here's a hypothetical nightmare. Imagine that you have a bug where your label is broken. Now, model validation, if you're actually doing any type of offline analysis, all that stuff that you was just described in that last talk, well, if the label is actually incorrect, it's all meaningless. All the statistics doesn't matter, right? So that's absolutely critical that that label be correct. And without it, we have no safeguards whatsoever. So okay, so let's just do it. What's the problem? Well, we're balancing the safety and security of the system with basically the intention of our users who would much rather be building models. So one common case is that users, after building the system, after initial check through the data to look at what they're going to do with it, they don't look at it anymore ever again. And the data could keep coming in. Or you can imagine another extreme case where it's extremely secure, where they're checking it every day. Now, of course, we can't be as secure as if the users are checking the data every day, and we can't be as easy to use as not doing anything at all. So, but we want to do almost as well as both in each dimension. Does that make sense? Great. So, data expectations and a prescriptive schema are core to the system. What I mean by a prescriptive schema is it's something that describes the data. It does not describe the data. It describes what the data should be like. It tells it gives hopes for what the data should be. And that's in comparison to, say, the data statistics, which actually describe the data, and the trainer needs, which represent what actually needs to be true for the data to actually work for the trainer. And one thing that we have to recognize if we're building this is we can't just write a schema at the beginning and hope to extend it, it'll last forever. There's new features being added, there's features that break and we have to remove from the system, or we just don't find it as valuable as they used to be. So we imagine that these are going to co-evolve all three of these aspects, okay? So how do we design a system that treats users' time and attention as a valuable resource? This is the key issue here. We want to automate what can be automated. We want to ask the right questions at the right time. For example, during development, when we have that machine learning expert in the room, and not late at night when we have the person, whoever's on call and is watching over 15 models, and has to deal with a problem. We want to unify the system. We want all these different components to work together, and we want to understand how users are using our system. So this is part of a larger ecosystem, TFX, which is a production ML platform for everyone. We've recently been open sourcing parts of this, and hundreds of teams use it throughout Alphabet. And today I will describe some of the safety measures in that system. So as Scully pointed out before, the machine learning requires much more than training. That ML code is a teeny bit in this larger view. And today I'm going to be talking about data verification, analysis tools, and monitoring. And then specifically, I'm talking about model unit testing. And if you don't know what model unit testing is, I'll talk to you about that right now. So next I'm going to talk about the life of a schema, model unit testing, inter-batch agreement, how to deal with changes over time and differences between inference and training data. I'm going to talk about the telemetry that we've gathered over those hundreds of teams who are using the system, and then I'm going to conclude. So beginning with the life of a schema. Before I talk to you about what our schema is, I want to talk to you a little bit about what TensorFlow data looks like. So specifically, we have the number of visits. For instance, we have this protocol buffer, which looks a lot like a JSON object. And for each feature, there's a key, which says which feature it is. And then there's a value, for example, which is either an integer array, or it's a bytes array, or a string array, basically, or a float array, okay? And notice that if we have a single value, we don't know that it's a single value, but it's just an array of length 1. So what kind of schema do we use to describe that data? Well, first of all, we say what kind of object it is. We say the value count, and then we give some presence constraints. Like for instance, is it always present? Then we say the min fraction is 1.0. And how do we make sure that everyone has a schema for their data? Well, it's a very simple answer to that. If you don't have a schema, we'll generate one for you. Now, we have to keep in mind that if we generated a schema for somebody, it was somebody who didn't want to provide us with a schema of their own, and so therefore we should be a little bit more conservative in the kinds of anomalies that we are going to throw. So, but this actually does start to connect the data. So when you have the data, we can automatically generate a schema, and once we have that schema, we can validate the data. So here's the first kind of schema that we can, or type of feature we can generate. Here we automatically infer the data type. That's unlikely to change. If there's only one value per example, that's incredibly useful for a modeler, so we throw that in there. And it's also very unlikely to change. And finally, if it's always present, then we throw in a min fraction of 1.0. Right? So these are the kinds of simple checks. But as I pointed out, a lot of times the feature is just completely missing. That's the kind of anomaly you're facing. So these kinds of simple checks are very useful and powerful. Another kind of thing that we do that's helpful for people building models is we identify that it says it's a bytes value, but in fact, if you look at all the values, it looks like it's probably representing a Boolean because it's set and clear, or true and false, or a string of 1 and then 0. You get the idea. And then finally, if there's a small number of string values, then we represent it as a string domain. So this is very useful information, not just for data validation, but also for the system as a whole, when you're thinking about how to transform these features, how you're going to use them in your model, and so forth. So now, auto-generated schemas can be edited. So if you have some user who's just really excited about putting everything, checking everything, and having lots of anomalies fire, then you can handle that. So for example, they might add the int domain to have a min of 0. And then making sure that there's no visits is always positive or always non-negative. Now, suppose that there's a problem with the schema or a problem with the data. And specifically what I mean by that is the schema says that the min fraction present must be 1.0. But the stats say that the fraction present is actually 0.9. So what's wrong? So we're not sure if the data is bad or if we need to fix the schema. Now, if the data is bad, there's a long, drawn-out process that we'll have to go through. But if the user just looks at this and says, you know what, I don't really care that the min fraction is 1.0, I'm just going to fix the schema, that's something that we can do very easily. So when we're fixing whenever there's an anomaly, one thing we provide the user immediately is a modification to the schema that just makes the anomaly go away. And this is incredibly important, because if you don't make it really easy to deal with your mistakes, then users won't use your system. And so we have to make the system very usable. Negative values, if the int domain is violated, we just provide a new, we fix the schema so that it includes that data. And multivalency, similarly. And if it's completely missing in the data, or for instance, if it used to be an int type and now it's a string type, we just mark it as deprecated. And then we're forcing the user to say, all right, either you don't care about this feature, or you're going to go back and fix it. All right? And so this completes the story of the connection between the data statistics and the data expectations in our schema. And by anomalies that when they occur, are represented as schema updates that can then be directly applied to the schema. So everything is we're unifying the entire system. So the next aspect is model unit testing. So in particular, when you have, we're doing this coevolution, we're focusing on the data statistics and we're making sure that we're not firing too many anomalies. But then how do we know that we're firing enough, right? How do we know that, like for instance, maybe the data won't actually work with the trainer. Maybe there's a num visits of 0 and the trainer has a log num visits, and that's gonna cause us serious problems. Well, if that happens during development, it's not a big deal. We'll just fix it, right? We'll add 1 or whatever to the num visits. However, if it happens during development, then doesn't happen during development, but it happens in production when there's somebody else late at night and they have to deal with it, that's a problem. And moreover, it's a very serious problem because they don't know whether or not your trainer is broken or the new data is broken, which makes it an incredibly difficult problem to solve. So our solution here is that when you're developing the model, we do model unit testing where we take the schema that you generated and then we generate data that satisfies that schema and then we feed it into the trainer. And so in an ideal scenario, the current data is a subset of like all the data that you're gonna see in the future. And it's a subset, and that is of course a subset of all the valid data based upon the schema. And that is a subset of all the data the trainer can handle. Now, if we do fuzz testing, we're going to generate a whole bunch of examples that are valid data based upon the schema. And they should all be data the trainer can handle. And if they're not, we get some examples where the trainer can't work. So in particular here, we have, if the num visits is 0, well, that looks like a perfectly valid example. We need to fix our trainer. But if we said num visits is -2, oh, okay, well now we actually have to fix the schema and add a constraint. So we can basically go through with this, and now we have a better schema. So if we do in development have an error, if it violates the schema, then we know that we have a problem with the data. Or if it passes the schema, then we know we have a problem with the trainer. At least that's where we want to start looking, and we have a lot more confidence in how we start our debugging process. So this is basically our coevolution of data statistics and the schema and the trainer. And basically there's all these connections and the system is unified and things are automated when they need to be automated. It's a very easy system to use. And in particular, they fit into the larger TFX ecosystem And so now I'm going to talk a little bit about inter-batch agreement. So suppose that you have, you get training data and it's arriving over time. And you have the training data from yesterday and the training data from today. And you don't want it to change too much. Moreover, you have your inference data as well, the data that you might be drawing directly from as you're doing inference. So you want to make sure that inference and training are the same, right? Just like practice like you play. However, it's not always possible. So for instance, there's an inherent skew in ranking problems where you just can't get the label of all the examples that you need to perform inference on. So we have to allow for some difference. Moreover, yesterday and today, if you think about yesterday and today, one natural thing to do would be to say, today was generated from the same distribution as yesterday. And if you have like maybe 100 examples coming a day, you might be able to make that assumption and not be able to invalidate the null hypothesis. However, let's suppose you have 100 million examples coming every day. And there's a very small change between yesterday and today, which is completely reasonable. Maybe there's 10,000 examples that change their norm from 1 to 2. Well, then you're going to invalidate the null hypothesis. You're going to say, oh, there's something wrong here. And when we tried this with real data sets too, using chi-squared test, we got the same results, that you would invalidate the null hypothesis all the time. So you can't use this as an assumption. So here's a solution. We bound the L infinity distance from yesterday to today. So specifically, we look at the distributions and we just use the L infinity distance as a metric. This has a variety of practical advantages. So for instance, keep in mind that the scientist who designs the anomaly detection system is not necessarily the same person who has to deal with the anomaly as it arrives. So the L-infinity distance doesn't just give you a distance, it also gives you a witness. So here you're seeing the country that all the examples are coming from, and you see a 3% increase in India, and so you're asking yourself, well, here's the witness. The India changed by 3%. That's why I'm getting this anomaly. Is that okay? And so somebody who's a little familiar with the data might be able to handle that. They don't have to necessarily be a machine learning expert to be able to understand that kind of anomaly. So now for the fun stuff that you're all waiting to hear before you go over to lunch. So changes to the schema. So are people actually using this thing? Well, almost a little less than half of our users take the original schema that's either automatically created or they've manually inserted, and they leave it with that, and they don't ever change it, right? But then many of our users do make edits and changes to the schema. Moreover, the anomalies that occur, do fire. Like in a month, in a period of a month, like maybe 10% of the new feature column anomalies fired. And then when they did fire, like, about 2/3 of the time they were getting fixed. So if you'll notice, most of these anomalies that are firing are feature churn, because that's a very common thing. It's a part of a natural, healthy environment that features are going to be added and removed. But that doesn't mean that you don't want to check when a feature suddenly disappears that it was supposed to disappear. Out of domain values is another common one. So if you're listing all the values for a particular feature, you're going to have an anomaly anytime a new feature, a new value occurs. All right. So I think a big picture here is people are dealing with the system. They're handling the anomalies, but they're not handling all the anomalies. So we could improve the system and make it easier to use and have people handle more of these anomalies. So in conclusion, there's a bunch of open questions. Like for instance, but I think the most important one here is this. If we want people to deal with anomalies, we have to justify why they're dealing with anomalies. So how do we estimate the return on investment of fixing a problem before it's fixed, before we've actually asked the user to fix it? I think this is fairly straightforward for things like missing features, but if you think of more general or of more specific types of anomalies, it's a lot harder. And some other future work, time series anomalies, like taking the more important parameters of the system and tracking them using a time series and making sure that they're what we expect. Extending fuzz testing to inference. We've done some work on that internally and hope to make it available. Automatically tune the schema during fuzz testing. Automatically infer semantic types. Deeper understanding of feature usage in training and inference, not just black box testing. So in general, remember, watching for silent data failures is something that you don't have to think about a lot if you're building an email system, but if you're building a machine learning system, it can give you huge wins. And we have to design a system that treats users' time and attention as a valuable resource. So we have open source software. Feel free to take a photo of this page if you like, or just search TensorFlow data validation. It'll get you to where you need to be on your favorite search engine, of course. If there are any questions, I also have more case studies if you'd like to hear about them.
Okay, we have time for a few questions.
Hi, I'm Hua Zhang from Netflix. I actually have two questions. The first question is, actually after we obtain the data, there are a lot of transformations, data transformation, feature transformation. All those transformers can be faulty too. So where do you think we should put the probe on? Right before the trainer or right after data acquisition or somewhere in between?
Yes. So you should put it before the trainer. I think that's an important part. I think you also want to, so for instance, keep in mind, one of the things that really messes with you is when the trainer, when the data itself is wrong. If you won't necessarily have the right idea, there's no way for a new model to compensate for that. But on the other hand, yeah, you want to make sure that your model itself is doing as well as it could. So you can put anomaly detection there as well. Another nice thing about having the post-transform anomaly detection is that it's much easier to sort of, like I was talking about the ROI, it's much easier to estimate the ROI if I know the statistics right before the data goes into the model. So specifically, if you're doing something like flattening the data, right, and then you know that this feature is in 10% of the, or it's in 90% of the data, and then it suddenly goes to 2% of the data, that's a very important, that's very important information to have. And so, and internally, we do have both of those types of anomaly detection available. Did you have a second question, or was that, have I not heard that?
The second question would be, in your paper, you say you got this schema from some heuristics. Why don't you train a simple model for that? Say a very simple LR model for better ROI. I don't know.
So, I think this allows me to say one of my favorite things about machine learning. It's like, well, what is the actual objective of that model, right? So, how do you weigh off false positives? There's all sorts of questions. I mean, I think that telemetry is a beginning to get there, but I think I would love to hear from you or other people. What is the right objective there? It's hard to quantify, but we have an idea of simple things that are easy to. And how do you quantify easy to understand objectives, right?
All right. Thank you very much.
Thank you.
Hi there, Nikos from Quantum Black. Thanks for the talk. Two questions. A quick one is this protobuf specific? Does it work with pandas, PySpark data frames?
So one thing no, it is not protobuf specific. It is, so there's I mentioned this in the Coevolution, there's data statistics. So we take our original data and like calculate statistics. So we have ability to calculate statistics for like CSV and the Tensorflow example. If you can calculate the statistics for whatever data you have, then you can run this system on that. So I mean, it's just there'd be more work obviously, but yeah, there's nothing protobuf specific. Like if I remember correctly, the kind of thrift data formats look similar to the TensorFlow example formats that we have.
Cool. And the second one, you touched briefly upon generating mock data for unit testing models. It's easy to generate like this kind of data if you have simple predicates like min, max, nulls, distinct values, etc. Are you aware of any tools, or do you have anything in here for more advanced mock data generation, like specific distributions, correlations, time series, things like that?
I'll have to get back to you on that one. I'm not sure, but I mean, I think primarily we're focusing on like the thresholds and stuff like that. Like, because it's like, keep in mind also that we're not necessarily trying to calculate the performance of the model. We're trying to see whether or not that model will like the data will go through the trainer and will go through the model. Like if you were trying to do, I think that kind of analysis and that kind of those kinds of distributions would be more important if we were trying to actually do. Trying to actually see how the model will perform.
Hi, Musa from Quantum Black. Are you also trying to easily quantify the performance difference based on distributional changes in features?
Sorry, can you say the question?
Like changes in distribution of features, easily quantifying performance difference because of those distributional changes in features?
I mean, so I think that you're getting to that open question there, which is like, we have a schema that we've generated and we see if the data satisfies it. We can check and see if the model can work on the data that is specified in the schema. We do not necessarily, we're not checking the performance of the model. You can look at, so there's another team in the TFX umbrella that works on they have a product called TFMA, and you can look at that. I don't know whether or not they handle that, what you just described. But the TensorFlow model analysis would be where I would look.
Okay, let's thank our speaker again, and now we have a lunch break.